Hi, I'm Guoxi. I'm going to present our paper Behavior Estimation from Multi-Source Data for Offline Reinforcement Learning. This is a joint work with my supervisor, Hisashi Kashima. We consider offline reinforcement learning to solve sequential decision-making tasks. On the left, I show an example task. This is a boxing game. At each step, an agent takes as inputs the state S, which can be the current position of its opponent. It needs to select an action, say move left or right. The agent receives a scalar reward as feedback for this decision. Offline RL is a setting that develops agents using previously generated data. Suppose there is a database that stores data generated during previous agent training or human demonstrations. The goal of offline RL is to develop a new agent using these existing data, so as to reduce the cost of data collection. Let's talk more about the data in offline setting. One scenario is that the data can be collected from multiple sources. Here I include an illustration for a platform named RobotTurk. This platform tries to speed up data collection using crowdsourcing by collecting demonstrations from multiple demonstrators. In this case, the collected data are from multiple sources. Here's another scenario that I would like to talk about. Sometimes we can generate training data using a real system, but such data collection is very expensive, so it is unlikely that we try every design choice using the real system. What we can do is train one agent online and store the training data. Then we can use the data to try out design choices, such as different algorithms and architectures. I would like to emphasize that even if the data are from single source, they are generated by different policies. The reason is that during online training, the policy keeps improving, so two trajectories are likely to be generated by different policies. Now, I will talk about the task we address in this paper. Behavior estimation is a task of estimating the data generating policy. The current approach is to estimate a single policy using maximum likelihood estimation. So suppose you have a policy parameterized with neural networks, theta b. The current approach is to learn this network by maximizing the likelihood of actions given states. Recently, there are extensions to this approach, usually by using more complex parameterization for the behavior policy. Behavior estimation is critical for many algorithms. For example, in the literature of offline RL, there is a line of work that penalizes the output policy for deviation from its behavior policy, which aims at stabilizing the training process. Such algorithm require an estimator for the behavior policy. Another example is importance sampling, which requires the behavior policy to compute the importance weights. However, on multi-source data, the current approach faces a challenge. On the left, I show a very simple example to illustrate the challenge. Here, the data are generated by two Gaussians. If we feed a behavior policy using single Gaussian, then we will place the probability mass in the regions that are not covered by data. On the right, I show the performance of some algorithms on the D4IL datasets. The numbers is the performance percentage to expert policy. The medium versions are generated by a single policy, and the medium replay versions are the training data for the IL policy. So the medium versions are single-source data, while the medium replay versions are multi-source. As for algorithms, the FBRAC algorithm estimates the behavior policy using a mixture model. The MOP algorithm uses the ensemble of autoregressive models. Note that both of them use mixtures. The BRAC-V algorithm uses a single Gaussian policy. You can see that all three algorithms perform worse on the medium replay versions of Walker 2D and Hopper. These results show that the current approach for behavior estimation faces a challenge on multi-source data, and this challenge cannot be simply solved by using mixtures for action distributions. Our approach is to estimate a behavior set and a matrix that assigns trajectories to the elements in this set. To this end, we propose a generative model for multi-source data and a learning algorithm. We showcase the proposed model by incorporating it into the BRAC-V algorithm. Here is a graphical model representation for our generative model. It assumes that each trajectory is generated by a single policy. So to generate tau m, first you sample an assignment variable zm from 1 to k. Then all the actions in this trajectory are generated by the policy bzm. In some sense, our proposed model is still a mixture model. This slide illustrates its difference from the existing model. On the above, I show two state action pairs in the same trajectory in our model. The actions are deconnected by ZM, which means that knowing each action provides more information about ZM. On the below, I show two state action pairs in the same trajectory in existing mixtures. Note that, as they assume action distributions on each state is a mixture, each state action pair has different assignment variable z. The consequence is that knowing AMT provides no information about ZMT prime. However, as the two actions are generated by the same policy, such independence is unrealistic. Intuitively, good policies tend to produce good actions, and bad policies tend to generate bad actions. Now I will explain how we parameterize this model. Although we try to estimate k behavior policies, learning k different networks is too expensive, and that won't allow us to explore information that is common to all behavior policies. So we learn the embedding matrix E for the policies and share neural networks among them. Each row of E represents the policy. Given state, we first maps it into a vector using network Fs. Then the vector is concatenated with the embedding vector of the corresponding policy and passed to another network Fp, which outputs action distributions. In addition, we also learn the Q functions of these policies, which can be used in actor-critic algorithms. To compute the Q value of a state action pair in some trajectory, we first map the pair into a vector using network FSA. Then the vector is concatenated with the vector in the matrix H and passed to a network FQ. We decide to learn the model parameters using variational inference, but the challenge is that the behavior set is discrete. It is unlikely that we can use amortized inference, which computes posterior estimates with a function. We addressed this challenge using quantized variational inference. We assume that a matrix W has variational parameters, whose rows are representations for trajectories. Then, the posterior distribution can be formulated like this. It computes the distance between Wm and the embeddings of all behavior policies, and it places all the probability mass on the behavior policy that is the most close to Wm. Here is the learning objective. It contains three terms. LREC encourages action reconstructions. Let ZM tilde be the posterior estimate of the behavior assignment for the mth trajectory. So, EZM tilde represents the policy that generates tau m. The term shown in green encourages reconstructing actions in the mth trajectory using this vector. The term shown in blue is one key of our quantized variational inference. This term encourages Wm to reconstructing actions, which makes it a valid representation for trajectories. LCOM penalizes deviation of ZM tilde from Wm. This is to ensure that the two vectors satisfy the posterior shown in last slide. In some sense, you can consider it as maximizing the data likelihood. Together, LREC and LCOM achieve that every trajectory is assigned to some behavior policy, and the behavior policy can generate the trajectory. The last term LQ is just used for learning the Q functions of the behavior policies. To showcase this model, we use it to extend the Bragg-V algorithm. The ideas are twofold. When computing loss using transitions in a trajectory, compute the regularization using the corresponding behavior policy BZM tilde. And we share Fs, Fp, Fsa, and Fq with the output policy. Here are part of our experiment results. The x-axis of each figure denotes the number of behavior policies for the data. The y-axis denotes performance ratio between the output policy and the behavior policy. As expected, Bragg-V, shown in orange, becomes worse when data generated by multiple policies. One interesting observation is that the CQL algorithm, shown in blue, also performs worse on multi-source data, even if it does not rely on behavior estimation. On the contrary, the proposed L-Bragg-V, which is shown in green, has robust performance, and two other VAE-based algorithms, PLAS and BCQ, are also robust. Here is another part of the experiment results. The proposed L-Bragg-V has good performance on both medium and median replay versions when compared to other VAE-based methods. It also significantly outperforms BRAC-V, which shows the efficacy of our proposed model. Here's a summary of our findings. The performance of existing algorithms worsen on multi-source data, including those that don't need a behavior estimate. Algorithms that learn a latent space for actions have robust performance. With the help of the proposed method, BRAC-V achieves state-of-the-art performance on multi-source data. Thank you.